Let's solve exercise 7 next, where we have to prove theorem 12, 5, 10. So let's first recall theorem 10. We start with a metric space, of course, x comma d. This is part A. There are also parts B and C. In A, we have two subsets y and z of x, where z is a subset of y, and it's given that y is compact. Then this is the claim. Z is compact if and only if z is closed in y. Although we are proving a theorem, but because this is an exercise solution, so I have written solution. So in this part, we will prove this part A, and then we will prove parts B and C afterwards. Now recall from corollary 12, 5, 6 that in a metric space, a compact set, or in other words, a compact subset is closed and bounded. In particular, if Z is compact, then it's also closed in Y. Conversely, let Z be closed in Y. Now we need to prove that Z is then compact. And for that, we choose a sequence Zn in Z. Now what is it that we need to show? We need to show that this sequence has a subsequence which converges to a point in Z. Now what is the relationship between the sets Z and Y? Z is a subset of Y. So this is a sequence in Z, means it's also automatically a sequence in Y. And what is given? Y is compact. So that's why, by the definition of compactness, this sequence will have a subsequence which will converge to some point Z in Y. But then by a previous result, the point Z becomes an adherent point of the set Z. In other words, it belongs to the closure of Z. This closure has been calculated by considering Z as a subspace of Y. But anyway, what else is given to us? That Z is closed in Y. So this closure is nothing but Z itself. So that's how the point Z belongs to Z. So what have you achieved here? You started by choosing any sequence Zn in Z. You have then found a subsequence which converges to a point in Z. So that's why by definition Z is compact. So this completes the proof of part A. Now let's go to part B. This is part B. Part B states that if these yi's are compact subsets of X, finitely many of them, n number of them, then their union is also compact. In other words, the union of finitely many compact sets in a metric space is also compact. In the solution, we first observe something which simplifies things immediately. It's enough to only prove the case n equal to 2. That is, you just have to prove that the union of two compact sets is compact, because then the general case will easily follow from induction. And accordingly, let Xn be a sequence in Y1 union Y2. We now need to show that then there exists a subsequence of this sequence which converges to some point in this union. Now next we have this. We assume without loss of generality that there exists a subsequence Xni of that sequence, all of whose terms belong to Y1. But why? To understand why, let's look at this diagram. This is of course a Venn diagram showing Y1 and Y2. It may look a bit misleading because it indicates that Y1 and Y2 do not have any intersection. That's not necessarily true. There may be intersection, but because what we are going to discuss here has nothing to do with whether Y1 and Y2 have or don't have any intersection, so I just decided to draw like this. Now you look at the terms of the sequence. Say you concentrate on x1 first, that is the first term. Because the sequence after all is a sequence in y1 union y2, so x1 needs to be a point in the union, and as such it will belong to either y1 or y2. Anything can happen because our sequence is general. Suppose x1 belongs to y1. What about the next term x2? That also belongs to either y1 or y2. Say x2 is not in y1, then it has to be in y2. x3 is say in y1, okay. x4 is also in y1. So like that, you can have anything can actually happen. Now the point is that, is it possible for both the sets to have only finitely many xi's, each one of them? That of course is not possible, because there are infinitely many terms in this sequence. So there should be at least one set between these two which has to have infinitely many terms of the sequence. Not necessarily all of them, but infinitely many. And when you take them together, they form a subsequence, obviously, of the original sequence. But why are we saying that that is the set y1? It can be y2 also. That is why we have written, we assume without loss of generality, let y1 be that set which has infinitely many terms of the sequence. Actually, with this, y2 can also have infinitely many terms of the sequence, or finitely many. Okay, anything can go, but the point here is that one of them has to have a subsequence like this. So we have just simply called it y1. That's it. So we then continue, because y1 is compact, y2 is also compact, but right now we are inside y1, which is compact, and this is after all a sequence in y1. So it will have its own subsequence xnij. Don't get scared by these suffixes, okay? We are not going to continue with more suffixes. This is where it stops. But anyway, this is a subsequence of this subsequence that converges to some point x in y1. This subsequence converges to some point x in y1 due to the compactness of y1, and due to the fact that this subsequence is a sequence in y1. Hence, this subsequence becomes a subsequence of the original sequence as well. A subsequence of a subsequence is after all a subsequence of the original sequence that converges to this point x, which is also in y1 union y2, but then by the definition of compactness, y1 union y2 is compact. Strictly speaking, the solution to part B does not really stop here. You have to extend it to the case of any finite number of compact subsets and their union being compact by induction. Okay, so you have to prove that. Please do it. And finally, we have part C, which states that every finite subset of X, including the empty set, is compact. Compactness of the empty set is trivial. Actually, if you apply the definition of compactness to the empty set, then the condition for compactness becomes vacuously true, but true nevertheless. So that's why the empty set is compact. So next, that means we have to prove that every non-empty finite set is compact. For that, we apply a trick. We don't go for a general finite set, non-empty finite set. Instead, what we do, we consider any point x in X, and then we consider this one point set having its only point x. Let's show that this is compact. So that means we have to choose a sequence in it. Now the only sequence you can think of in this situation is this constant sequence, all of whose terms are equal to x. Now clearly the sequence is a subsequence of itself, and which is also of course convergent, because it's the constant sequence, so it will converge to x, which is a point in this set. So by the definition of compactness, this set is compact. Hence, by part B, any non-empty finite set is also compact. But how does this last line come from this one and part B? That's actually quite easy. Say you take these 3 points in X, which are, say, distinct, and consider this 3-point set. It's the finite non-empty set. This set is equal to the union of its 1-point subsets. What did you prove just now? That each such subset is compact. So by part B, this union is also compact. That's how.